So in this lecture, we are going to really start looking at some of the really important concepts, really moving into really juicy topic in statistics in which we're making inferences. We're actually starting to run different statistical tests to answer your research questions. So for the rest of the semester, everything else we're going to learn in statistics is really going to build on what we learned in this lecture. So you really want to make sure you master this lecture very well. So first, let's take a look at some assumptions. We're going to make some conditions before we start thinking about inferences. Now, another thing I want to point out, if you haven't caught that on from the previous lecture, is that we really want to focus on the mean now. So we're moving away from categorical variables and looking at continuous variables. So the parameter of interest now would be population mean. So in this lecture, you can see here it says note that we are going to pretend that we know the population standard deviation, which I guess my question for you is, what is the notation for the population standard deviation? That is sigma, right? So these are parameters you should be really familiar with at this point. This is your population standard deviation. This is your population mean, also known as mu. So you're going to hear me say that a lot. So for this lecture, you want to know your conditions are given to you right here. We have a random sample, and we are going to say that we know what the population standard deviation is. We know what sigma is, but we do not know what population mean is. So the goal of this lecture is for us to really kind of estimate what population mean is, using what? Using X bar to help us estimate what the population mean is. You know, obviously in the real world, we do not know what sigma is, and we'll learn in another lecture what happens when we don't know what sigma is. What do we do with that? But for now, let's pretend that we know what sigma is. So in the slide, it should look really familiar, right? We worked with confidence intervals previously, looking at proportions. So you know that here's an example of, again, proportions because it tells you percentages. So for example, 54% of teenagers get along very well with their parents, right? So you have a 95% CI for the population proportion, right? Keywords for you to know here is population proportion, your confidence interval. It's about the population proportion. It's not about your sample. Your sample is calculated in front of you. Everything that you have from your data is about the sample. So there's never a need for you to estimate what a sample is. So let's take a look at what that confidence interval structure is. Again, a little review of confidence interval because we're going to work with CIs for the rest of the semester, but for different parameters. So here you can see we have the structure that does not change at all for a confidence interval. It's always going to be your point estimate plus minus the margin of error, right? So from the previous confidence interval we worked on, you know that point estimate for proportions is what? If you remember, that's going to be p hat, right, plus minus 1 over square root of n. That was for the 95% confidence interval for a proportion. Now again, in this lecture, we want to estimate what population mean is. We want to estimate what mu is. But we're going to use this very same structure to calculate confidence intervals. Right, and here on the bottom you should see that the most common level is 95%. So most of the times when you're picking up a peer review article, you're reading in some journal article, the most common level you're going to use is 95%. But after learning this lecture, you should feel really comfortable with confidence intervals that you can calculate an 80%, an 85%, a 99%, 68% confidence interval, and we'll learn how to do that. Right, and when I say 68 or 90%, I'm referring to what? Different levels of confidence, so different C levels. Level of confidence is something you can decide as the researcher, you can decide as the statistician what level of confidence you want to use. But, you know, I really recommend that you stick with the 95%. So here we have an example of a 95% confidence interval for what? For the population mean, for mu. Right, it tells you right here, for mu, we're trying to estimate what that mu value is. So we are using our CI formula, right? Point estimate plus minus. Now look very carefully here. Your margin of error now is composed of two things. First, a critical value times by your standard deviation of your statistic. Right, so I'm going to take a second for you to look at that and think, well, you see here, this is now your point estimate. This is your sample mean, right, x bar, similar to the idea of p hat, but that was for proportions. Now we're looking at continuous variables, so we're working with x bar. X bar plus minus margin of error, right? The margin of error is now made up of, this in blue now, this is your critical value, and this is your standard deviation of statistic. So your z star is always going to be your critical value, and that's something you can actually look up on a table. So if you want to pause this lecture and pick up your t table on Blackboard, you see on the very bottom of that table, it will give you multiple levels of different z stars. So when I say z star, I'm referring to a critical value. So for example, a 95% CI will always have a fixed z star, right, if you're doing population mean. So z star, forever and always, that critical value is going to be 1.96. And this is something you're going to work with so much that by the end of the semester, when you see that z star for 95%, you're going to know it's 1.96. But that's something you can look up easily. The standard deviation is sigma over square root of n, and we'll take a look at that in a little bit. But that should really look familiar to you from the sampling distribution of x bar. Right, so that's our standard deviation of your x bar here, and that's how you can calculate a 95% confidence interval. So if I were to ask you for a 90% confidence interval, the only thing that would change in this equation would be your z star would be the only thing that would change. If it's a 90% confidence interval or 68% confidence interval, you would just have to change the corresponding z star. So if you were to take out your t table, right, so this is not the z table now, it's the t table. On the very bottom, you can see there's a z star, right, a row of z stars. So that's where you would go to look up what level of confidence you're interested in, so you can find the corresponding critical value. The critical value, of course, is your z star. You're going to use this to find out what z star is so you can calculate correctly the CI. So for example, when earlier we did 1.96, that's because we're looking at 95%, right? But if I ask for a 98% confidence interval, then now you're going to look up 98%, and you're going to see the new critical value is now 2.326, right? So if I ask you for 50%, what would that z star be? Your critical value would be 0.674 over here. So that's how you would decide what that critical value is. Now, when you look at the z star across from left to right, what do you notice about the z stars? As your level of confidence increases, what do you notice about the critical value here? Right, you see that the critical value, the z star, is increasing, right? It's getting bigger as your confidence level gets stronger, right? You're going from saying I'm 95% confident to now saying I'm 99.8 confident or 99.9 confident. And look what happens to your z star. It gets larger. So think about what that impact of an increasing z star has on your confidence interval. Assuming that everything else stays the same, assuming that your x bar, your point estimate, your standard deviation of your statistics stays the same, what will happen is your confidence interval will become wider, right? So that will actually give you more possibilities of values, right? So giving you more confidence reporting your estimate for the population mean. So now it's a little bit of summary of how confidence intervals behave. Now, you as a researcher, now you're going to use statistics in your research and your work and field work. You really can't get away from it, so you really want to fully understand. Right, first, let's focus on margin of error. The margin of error, like I told you, when we're doing population means is different from when we're working with proportions, right? Here it's made up of two things. We have your critical value times by your standard deviation. So you can look at this and say, well, I can manipulate how wide or how narrow I want my confidence interval to be based on what level of C I choose, what level of confidence I choose, right? If I choose a very high level, then you saw earlier yourself that as that confidence increases, your critical value also increases. But what else do you notice here in this margin of error? The margin of error here, you can also see it's very much dependent on, no surprise here, very important is your sample size, right? So the larger your sample size is, look what happens to that standard deviation. The larger that sample size is, the smaller your standard deviation, right? Because it's in the denominator and you take the square root of it. So here you can see as n gets larger, as your sample size gets larger, it really reduces your margin of error, right? And ideally you want that margin of error to be small because it tells you that you have really narrowed down your parameter precisely. Versus if you choose a very high level of confidence, right? We talked about having a very high value of a z star, your confidence interval becomes wider, right? So as it gets wider, it's actually going to incorporate more values, right? So your chances, obviously, you're giving you a correct answer is much higher, right? So it's a little bit of a trade-off here when you're thinking about it. So always in statistics, you want to think of trade-off is I'm willing to give up on this to get that, and that really depends on what your research needs are. So let's try an example together. So here we're looking at a Framingham study. So this is actually a very, very famous study if you've heard of it. It's a study done in Massachusetts, maybe around the Boston area. That's a very classic longitudinal study following the people in this town, right, Framingham town. And it's because of this study today that we've really established the reasons why we know so much about cardiovascular disease. So here we just have a small subset of this real data we have. We have a sample size of over 3,000, right? And the mean systolic blood pressure is 127 and a standard deviation of 19. I'm asking you to calculate for me the 95% CI. For here it says what? True mean, right? So it's really asking you to calculate for me, what am I asking for? Mu, right? So take a moment, maybe pause the lecture and see if you can calculate for me what you think the confidence interval is, right? Maybe figure out what is the critical value, what is X bar, so on and so forth. So you can see it's actually really straightforward to calculate the confidence interval once you figure out what the critical value is. Everything else is given to you, right? Your point estimate is your X bar, is your sample mean, which it tells you is 127.3. This is X bar. Your critical value, you can find this on your T table. You know for sure the 95% corresponds to 1.96. And you plug in sigma, which is of course given to you, right? And the square root of n, and boom, you have your confidence interval down here. Always write from small to large. So the lower boundary is first, and then the upper boundary is here. What do you notice about this confidence interval? Would you say this is a very wide or very narrow confidence interval? It's a very narrow confidence interval, right? And you shouldn't be surprised to see such a narrow confidence interval because look at how big that sample size is. So this is really going to help you double check your work. If you have a very large sample size, you should expect to see a small margin of error. So here's a little learning check for you to kind of take a break and think about confidence interval. Can we only use it for means and not for other statistics? So hopefully this one was pretty straightforward because of course you can find confidence interval for other statistics, right? Because you just did that. We did confidence interval for p-hats, for proportions, in estimating for the population proportion. Now we're doing it for means. But you can also do confidence intervals for a difference in means, for two populations, for ratios, for odds ratios, for relative risk. So it's really something you can use for almost any statistics you're interested in.